Hello everyone, welcome to another episode of Math-221. So we didn't quite finish section 8.5, there were still some more things in there that we could have done, but we do need to keep moving along with the class so that we can finish in time. So we're going to go ahead and move on to chapter 9, and with section 9.1 and 9.2 today. Okay, so let's start with section 9.1. This is Introduction to Counting and Probability. Okay, so let's start with some vocabulary and some notation. So first of all, an experiment or a random process is a situation in which something random is going to happen, and then we're going to observe what happens. Typically, you can repeat experiments over and over again. So the first example here is flipping a coin, and then a second example is rolling a six-sided die. Now, I just want to insert at this point a little commentary. So we usually start off with these incredibly simple experiments like this, and I think this sometimes tends to give students the wrong idea that we actually care a lot about gambling or that we're even encouraging gambling. That's not really true. It's just that these are the simplest experiments that you can do, and then once we get our arms around these kind of experiments, we can build up to more complicated experiments that you would be able to use to model complex situations like, for example, epidemiology, spread of diseases, and things like that. Okay, so second vocabulary is the sample space. So sample space is the set of all possible outcomes of the experiment. So for our two examples here, flipping a coin, the outcomes are heads or tails, and we're just going to write those as H and T. And then for rolling a six-sided die, that's just the six sides, which they're numbered 1 through 6. Okay, then an event is a particular subset of the sample space that we are interested in, usually so that we can find its probability. So an event for flipping a coin could be getting a head, and then for rolling a die, an event could be getting a multiple of 3, so that would be 3 and 6. So those are subsets of the sample space. The probability of an event is the proportion of times we would expect the event to occur if the experiment were repeated over and over. So for flipping a coin, we assume that the coin is fair. In other words, it lands on heads half the time and tails half the time. So probability of getting a head would be 1/2 or 50%. And then probability of rolling a die and getting a multiple of 3 would be 1/3, because 1/3 of the outcomes are multiples of 3. So that would be 1/3 or 33.3% approximately. So you can express your probabilities, you can express them as fractions, or you can express them as percentages or as decimals, like 0.5. Either way is completely fine, it's totally the same. Okay, so let's look at our first formula here. This is the equally likely probability formula. So if S is a finite sample space in which all outcomes are equally likely, and E is an event in S, then the probability of E, which is denoted P of E, is P of E equals the number of outcomes in E divided by the number of outcomes in S. So this is something I think you probably already knew about, at least to some extent. Like on the last slide, we talked about how the probability of getting heads when flipping a coin is 1/2. So that's the top part is the number of outcomes in the event of getting a head, that's 1. And the bottom is the total number of outcomes in the whole sample space. So any result, which is heads and tails, or 2. So that would be 1/2. So this is pretty straightforward, I hope. The number of elements in a set, we had previously mentioned this just a little bit. That's called the set's cardinality, or its order. And we're going to use this notation right here from the textbook. So for any finite set A, n of A denotes the number of elements in A. So this is a function notation. N is like a function that you're plugging the set into. And the same for the probability. The probability notation is also function notation. But I do want you to know that this is actually not the most common notation for cardinality. The more common notation that you'll see out there in the world is this one. So the double lines on either side of the set name. So that notation, it looks just like absolute value, and it looks like that for a reason. This notation with the 2 lines is really commonly reused all over mathematics to stand in some way for the concept of size. So absolute value itself is kind of like a measurement of size. It's giving you the magnitude of the number without the sign. And in the same way, this notation here with the 2 lines on either side of A, that is also standing for the size of the set A. In other words, the number of elements that are in it. Another common notation is this one with the little number there, and that just stands for the number of things that are in A. So we'll stick with the book's notation with the capital N, but just be aware of these other ones because you will encounter them in other math classes. So using this notation, we would write the probability formula as this. So probability of E is the number of elements in E divided by the number of elements in S. Okay, let's do some examples. So first of all, I want to go over the sample space for when you're rolling two dice, that is. So a lot of common counting and probability problems involve dice and cards and coins and things like that, so you'll want to familiarize yourself with these sample spaces. So for the pair of dice sample space, it does have 36 possible outcomes. So you can think of the first die over here is giving you the rows. So this row, the first die is 1 in all of them. In this row, the first die is 2 in all of them, and then so on and so forth down the side here. And then the second die is being given on the columns. So in this column, they're all 1 on the second die. Here they're all 2 on the second die, and so on and so forth. So it's just a little table with 6 by 6, which is 36 outcomes. Do notice that all of these outcomes are equally likely, but one interesting feature is that some outcomes appear twice in both orders. So for example, here we have 3 on the first die and 1 on the second die, and then here we have 1 on the first die and 3 on the second die. So that is considered 2 separate outcomes. But then on the other hand, for like 1 and 1, that you only have 1 outcome that's like that. So we could say that it's twice as likely that you would get a 3 and a 1 in either order as it is to get a 1 and a 1. So that's something interesting to note about this. Okay, let's do an example where we use this. So in 7 through 10, use the sample space given in example 9.1.2. That's just this table that I've put down here for you. Write each of the following events as a set and compute its probability. So number 8, the event that the numbers showing face up are the same. So I'm just going to circle those for you. So it's these ones. Oops. So it's those 6 right there. So for the event, the way I could write it is I could do it as ordered pairs like this. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. Okay, and then the probability of that event. So there's 6 elements in the event, and then there's 36 elements in the whole sample space. So that's 6 over 36, or 1/6. And you can write those answers as fractions, or as decimals, or as percentages. Whatever you want to do is fine with me. Okay, let's look at the second one. The event that the sum of the numbers showing face up is at least 9. So there's an interesting little pattern to this table, and I will show it to you. So if we look at these 3 right here, these 3 sum up to 10. And if we look at these 2 right here, these 2 sum to 11. And then this is the only one that sums to 12, of course. And then there's also, for at least 9, that includes 9, so we gotta include this diagonal as well. So the equal sums are on the diagonals, which is kind of interesting. Okay, so for my sample space here, my event, I'm gonna write it like this. So I can have 3 and 6, or I can have 4 and 5, or 4 and 6, or I can have 5 and 4, 5 and 5, or 5 and 6, and then finally I could have 6 and 3, 6 and 4, 6 and 5, or 6 and 6. Okay, so I think that's 10 different outcomes that match this event. So the probability here is going to be 10 over 36, and if you want to reduce that, you can. It's not like necessary again, but you could reduce it like that. Okay, so here are a couple of homework problems for you to do with dice. So go ahead and pause the video and do these, and check your answers in the back of the book. Okay, so now let's talk about the standard 52 card deck. So this is, I should say, they're calling it standard, but it's really the standard American, and I believe it's also the one that's used in France. So all the different countries have their own style of playing cards, like Italian and Spanish decks, they actually have different things on the cards and different suits and ranks and stuff. So this is the standard American version. So I want to go over this deck with you, even though this might be like too basic for some of you, but I know that not everybody grew up playing with this deck, and you might not have known all of the details of it. So let's go over this and make sure we all understand how this deck works. And this is going to make really good examples for us, because it's easy to find lots of different events that are subsets in here. So first of all, there's 52 cards, and 52 is 13 times 4, and if you look at the table, there's 13 columns and 4 rows. And then each card has these attributes that are listed here. So each card has one of the 4 suits, and the 4 suits are these. So this row right here, this is the clubs, and then this row is the spades. This row is the hearts, and then this row is the diamonds. And like I said, in other countries they have some different ones like swords or cups or things like that. So the clubs look like a little clover. The spades, it's like some kind of stylized dagger. It does look a little like a spading or a shoveling implement, I suppose, if you want to think of it as that type of spade. And then hearts and diamonds look like what they are, which is useful. Each card has one of the 13 ranks. I think your author might also be calling that denominations or something like that, which is a non-standard term. But those are also called denominations. Okay, so the 13 ranks are the numbers 2 through 10, and then Jack, Queen, King, and Ace. So these ones here in the first column, those are the aces, and then these are the jacks, these are the queens, and these are the kings. Okay, and then each card has one of the 2 colors, either red or black. So all the hearts and diamonds are red, and then all the spades and clubs are black. You can kind of remember that because the red ones are like a nice thing that you would like to have. So they're red, like the color of love. And then the black ones is like something a black-hearted person would do, like club you over the head or hit you with a spade or something. I don't know. That's a dumb way to remember it, but that's how I remember it. Each card is then either a face card or not a face card, and that's completely literal. So the face cards are the ones that have the literal faces on them. So the aces are not face cards in particular. Okay, so that's how the deck works, and now let's do some examples. Okay, so for the first example, the event is the chosen card is black, and it has an even number on it. So the black even numbered ones are going to be these, the 2 2s, the 2 4s, the 2 6s, the 2 8s, and then the 2 10s. Okay, so let's see, how can we write this? If we want to do the notation, I think we could do like 2C for 2 of clubs, 2S for 2 of spades, and then 4C, 4S, 6C, 6S, 8C, 8S, and then 10C, 10S. Okay, so that's our event, and it appears to contain 10 elements. So the probability of this event is going to be 10 over 52. So there's 52 possible outcomes, and 10 of them are in our event. And of course you can reduce that if you would like to. Okay, second example, the event that the denomination of the chosen card, I really don't like this word, I've never heard it called that, and I've played a lot of cards, that the rank of the chosen card is at most 4, counting aces high. So at most 4 means 4 or below. So that's going to include these ones right here. So we're not counting aces because they're considering aces. So I think I forgot to mention this on the other slide, but aces can either be considered to be below 2 or they can be considered above the king. They're usually not considered to be both at once. So in this case, counting aces high means aces are above kings and not below the 2s. Okay, so our event here is going to consist of the 2 of clubs, the 3 of clubs, and the 4 of clubs, the 2 of spades, the 3 of spades, and the 4 of spades, the 2 of hearts, the 3 of hearts, and the 4 of hearts, and then the 2 of diamonds, the 3 of diamonds, and the 4 of diamonds. Okay, so that seems to be 12 elements in the event. So the probability of this event is going to then be 12 over 52, which if you want to, you can reduce that to 3 over 13. Okay, so here's a couple of examples for you to try. Go ahead and pause the video, do these, and look up the answers in the back of the book. Okay, so now let's do some examples with coins. Suppose that a coin is tossed 3 times and the side showing face up on each toss is noted. Suppose also that on each toss, heads and tails are equally likely. Let HHT indicate the outcome heads on the first 2 tosses and tails on the third. THT the outcome tails on the first and third tosses and heads on the second, and so on. So part A is going to be your homework, and then part B, number 1, is also your homework. So I'm just going to go over these last 2 as an example. Okay, but they did already tell us that there's 8 elements in the sample space, so that's all that I need to do part B. So let's see, part B, number 2. So the event is at least 2 tosses result in a head. So that could be either 2 of them were heads or all 3 of them were heads. So let me write the ways to get 2 heads first. So I could get the 2 heads at the beginning, or I could get 1 head and then a tail and then another head, or I could get, oops, let me erase that. Or I could get the tail first and then the 2 heads, or I could get all 3 heads. So that is all the ways to get at least 2 heads. And so the probability of this then would be there's 4 in the event, and then there's 8 in the total sample space. So that is 1/2. All right, then for number 2, so the event is no head is obtained. So if there's no heads obtained, then that means all 3 must have been tails. So this is pretty easy. Just 1/8. Okay, so go ahead and pause the video and do those 2 homework ones, and then check those in the back of the book. Okay, so here is another problem. Go ahead and I would like you to do this entire problem for homework. Now, part B and part B number 2 and number 3 are not in the back of the book, so I'll, in just a moment after you pause the video, I will go over the answers to those 2. Okay, so if you've already done the problem, then let me give you the answers for the last 2 here that were not in the back of the book. So the event that at least 2 children are girls. So this is going to be girl, girl, boy, boy, girl, or boy, girl, girl, or girl, girl, girl. So the probability of this event, it's exactly like the coin flipping one. It's just going to be 4/8, or 1/2. And then the last one, the event that no child is a girl. So this one is just going to be boy, boy, boy. And so the probability for this, just like with the coin flipping one, is going to be 1/8. Okay, so now let's do another example. So this one involves drawing balls from an urn, which I do have to warn you is like a super common example in probability. Not because balls in urns are in any way important, but just because this is the type of event that you can use to model many, many different kinds of real world events. And it's simple enough that we can actually understand it completely. Okay, so an urn contains 2 blue balls denoted B1 and B2, and 3 white balls denoted W1, W2, and W3. 1 ball is drawn, its color is recorded, and it is replaced in the urn. Then another ball is drawn, and its color is recorded. Part A, let B1, W2 denote the outcome that the first ball drawn is B1 and the second ball drawn is W2. Because the first ball is replaced before the second ball is drawn, the outcomes of the experiment are equally likely. List all 25 possible outcomes of the experiment. Okay, so this is going to be a little bit time consuming, but I'm going to do it with a table. So I'm going to put the first ball on the rows, and then I'm going to put the second ball on the columns. Okay, so my columns are going to look like B1, B2, W1, W2, W3, and then on my rows, I'm going to have B1, B2, W1, W2, W3. Okay. So this is going to be really boring to watch me fill this in. So you can just go ahead and fast forward to the part where I've got this all filled in if you would like to. So I'm going to use the first ball to denote the first thing here. So this is going to be B2, B1, oops, not B3. Oh my gosh. Okay. I still can't use this pen, you guys. I'm sorry. I really hope you're fast forwarding and not watching this. But if you are watching this, I'll just tell you, this is the second time I did this because the first time I did it, PowerPoint ate my recording. Okay, so that is all 25 outcomes right there. And so let's go ahead and do part B. So part B, consider the event that the first ball drawn is blue. List all outcomes in the event. What is the probability of the event? So if the first ball drawn is blue, let me just actually circle that for you. So it's going to be these ones right here. Sorry, not, wait a minute. Let me do it like this. These ones right here. So that is part B. So the event is going to consist of B1, 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 B2, B1, W1, B1, W2, B1, W3. So those are all the ones that start with B1, and then the ones that start with B2. Okay, I believe that's all of them. Oh, I missed something, didn't I? No, I didn't. Okay, so that is 10 of them. And so the probability of this event is going to be 10 over 25. All right, so part C, let me actually switch to a different color. Okay, so for part C, consider the event that only white balls are drawn. So that it's going to be these ones down here. So that is part C. And I'll just write them out. So W1, 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 W2, W1, W3, W2, W1, W2, 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 that's a 2, W3, W3, W1, W3, W2, and then W3, W3. Okay, so the probability of that, there's 9 outcomes, so that is going to be 9 over 25. Okay. All right, so here is your homework problem. That's pretty similar to the last one that I did. So go ahead and give this one a try and check the answers in the back of the book. Okay, so that finished with section 9.1. So let's move on to 9.2, which is possibility trees and the multiplication rule. So first of all, let's talk about possibility trees. So when an experiment consists of several smaller experiments that occur in sequence, we can actually use a tree to keep track of the outcomes. So let's look at this example here. So example 1, how many different outfits can you make from 4 shirts, black, blue, brown, and white, 3 pairs of pants, black, blue, or brown, and 2 pairs of shoes, black or brown? So you want to think of this as a series of decisions. So first you're going to choose a shirt, and then you're going to choose pants, and then you're going to choose shoes. So this here is like step 1, and then step 2, and then step 3. Okay, so each time you make a decision, you're going to branch off. So you start here, and then you branch off depending on which shirt you picked. And then once you've got your shirt on, then you look at your pants, and then you branch off again, and so on and so forth until you get down to the end of the decision-making process. So I hope you can see here that each of these different lines through the tree would give you a different outfit. So for example, if I look at this branching process right here, so brown shirt, black pants, and black shoes, that's one whole outfit. Okay, so this is one outfit. So how many different outfits are there in total? Well, you just have to count how many ways there are to get through the tree. So you go down to the bottom and count, you'll find that there's actually 24 different possible outfits. Okay, so now let's look at a similar example, but a little bit different. So example 2, how many different outfits can you make from 4 shirts, 3 pairs of pants, and 2 pairs of shoes? And so it's the same amount of clothing as last time. It's those things that were on the last slide, but this time we're not allowed to wear black and brown together. So this makes a big difference because, for example, after I choose a black shirt, then I no longer have access to my brown pants. I have to either do the blue pants or the black pants. I don't have the brown ones there. And the same thing when I get to the shoes, I don't have the brown shoes there. So in both of these, I just have one pair of shoes that I have to put on. But on the other hand, for example, if I choose my blue shirt, then I can choose any of the pants. But my pants choice might also restrict my shoes. So if I choose the black or the brown pants, then I'm forced into that color of shoes that match them. If I have the blue shirt and the blue pants, then I do have my 2 shoe choices. So if you go through and count the possibilities here, this is actually only 12 outfits. So there's a big difference between these two examples, and this is going to be a difference in the formulas that we're able to use to count these two different types of situations. So what I want you to notice is that in example 1, we always had the same number of choices for pants, regardless of which shirt we had chosen, and we always had the same number of choices for shoes, regardless of which shirt and pants we had chosen. So the number of outcomes available to us on each step did not depend on the particular outcomes that we had previously chosen. Whereas in example 2, the number of choices at each step was different depending on which shirts or pants we had previously chosen, right? So like right here, I have 3 choices, but over here I only had 2 choices. So my number of choices depended on what I had previously chosen. Okay, so this leads us to the multiplication rule. So the multiplication rule says the following: if an operation consists of k steps and the first step can be performed in n1 ways, the second step can be performed in n2 ways, regardless of how the first step was performed, and so on and so forth, all the way up through the kth step, where the kth step can be performed in nk ways, regardless of how the preceding steps were performed, then the entire operation can be performed in n1, n2, ... up through nk ways. So basically, you just multiply together the number of choices that you have at each step, and that gives you the number of ways to perform the entire process. But this only works if you're able to do this little part that's in the brackets, the regardless of how the previous steps were performed. It only works if that is true. So like in example 1, when any of the 4 shirts, 3 pants, or 2 pairs of shoes are allowed, we do get that we can use the multiplication rule to find that 4 times 3 times 2 equals 24. That is the number of different outfits. But in example 2, when the number of choices at each step depended on the choice at a previous step, you just can't use this rule at all. You just have to do it a completely different way. And so far the only way we know is by actually drawing the tree. Okay. So let's do some examples based on that concept, and I'll show you how I like to do these in an efficient manner. So we have an urn, and it contains 1 blue ball labeled B1 and 3 red balls labeled R1, R2, and R3. A second urn contains 2 red balls, R4 and R5, and 2 blue balls, B2 and B3. So I'm just going to like draw a little picture of this because this is kind of confusing. So we have 1 blue ball over here, and then we have R1, R2, and R3. Oops, that's an R. And then we have another urn over here, and it has R4, R5, and then it also has B2 and B3. Okay. An experiment is performed in which one of the 2 urns is chosen at random, and then 2 balls are randomly chosen from it, one after the other without replacement. Construct the possibility tree showing all possible outcomes of this experiment. Okay, so let's do that. Part A. Okay, so for my first step it's going to be choosing the urn. Step 1, choose urn. And then step 2 is going to be choosing the balls. Okay, so step 1 is going to be urn 1 and urn 2. So this will be urn 1. I guess this is 1 here and this is 2. And then urn 2. Okay, and then step 2, I don't think I want to choose the 2 balls at the same time. I'm going to choose them one at a time. So step 1 is going to be step 2 is going to be choose a ball. Okay, so I'm going to have 4 choices from each of these. So this is going to be, let's see, B1, R1, R2, and R3. And then over here I've got R4, R5, B2, and B3. Okay, and then for my last one, it does say that they're done, the balls are chosen without replacement. So that means I only have 3 balls left to choose from at this point for each of these. So this is going to be 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2. So this is getting a little messy. 1, 2, 3, 1, 2, 3, 1, 2, 3, and 1, 2, 3. Okay, so if I chose B1, then my other choices are going to be R1, R2, and R3. And then here, if I chose R1, then my choices are B1, R2, and R3. If I chose R2, then I have B1, R1, and R3. If I chose R3, then I have B1, R1, and R2. Now over here on the other urn, if I chose R4, then I have B2, B3, and R5. If I chose R5, then I have R4, B2, and B3. If I chose B2, then I have R4, R5, and B3. And if I chose B3, then I have R4, R5, and B2. Okay, that's really sloppy, but I hope you get the idea. So part B, what is the total number of outcomes of this experiment? So let's look at this tree here. So at the beginning we had 2 choices, and then on the next step we had 4 choices regardless of which urn we had chosen. We always had 4 choices. And then on the next step we always had 3 choices regardless of which ball or which urn we had previously chosen. It was always 3 choices. So this is going to be 2 times 4 times 3, which is 24. Part C, what is the probability that 2 red balls are chosen? Okay, so now what we've got to do is actually go through these outcomes and see which of them were 2 red balls. So I kind of regret that I was using red before, and now I'm going to use a different color, but whatever. All right, so which of these were 2 reds? So let's see. I think these ones were 2 reds. These ones were 2 reds. Let's see, what else? These ones were 2 reds. And what else? These 2. This one right here, rather. This one. And then that was all of them, I think. Yeah, so I think that's giving me 1, 2, 3, 4, 5, 6, 7, 8. I believe 8. And then finally, part C. Oops, I'm sorry, that was part C. What is the probability that 2 red balls are chosen? There are 8 ways to get 2 red. And so that's going to be 8 over 24, which is 1/3. Okay, so here's a homework problem for you. It's quite similar to the last one. So go ahead and pause the video and try this, and then check your answers in the back of the book. Okay, so let's do another example, and then there's 2 on here that are also for your homework. So these are your homework right here, and then this is going to be the example. Okay, so part C, how many bit strings of length 8 begin and end with a 1? And in part A, it does tell us that a bit string is a finite sequence of 0s and 1s. Okay, so let me show you the way that I like to do these. So if I'm going to have a length 8 bit string, what I'm going to do is I'm going to lay out a little template for myself where I have 8 blanks, 2, 3, 4, 5, 6, 7, 8. And then I'm going to think about these as my 8 different steps of constructing the bit string, and I'm going to think about how many choices I have for each of them. Okay, so this is my first bit right here. And how many choices do I have for my first bit? Well, I've been told that the bit string does need to begin with a 1. So this is going to be 1 choice because it has to be 1. Okay, that's told to me in the problem. It begins and ends with a 1. So likewise for my last bit, I'm also going to have just 1 choice because it has to end with a 1. Okay, so then what about these ones in the middle? So like for the second bit, how many choices do I have? So I actually have 2 choices here. I can put 0 or 1, okay? And then for all the rest of these, I'm going to have 2 choices for all these as well. Either a 0 or a 1 for all of those. So now what I'm going to do is I'm just going to fill in the number of choices that I had for each of these. So 1 choice here, 2 choices here, 2 choices, 2 choices, 2 choices, 2 choices, 2 choices, and then 1 choice. And then I'm going to multiply these all together. And that's going to be my answer. Okay, so this is going to be 2 to the 6, which I believe is 64. And that's how you do it. So go ahead and pause the video and do part A and part B, and check your answers in the back of the book. Okay, so let's do another combined example and homework problem. So this one right here, that's going to be your homework, and then this one will be the example. Okay, so hexadecimal numbers are made using the 16 digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, B, C, D, E, and F. So they're denoted by the subscript 16. We did actually go over this in a previous section. So for example, these right here, these are hexadecimal numbers. So part B says, how many hexadecimal numbers begin with one of the digits 4 through D and end with one of the digits 2 through E and are 6 digits long? So I should mention that the hexadecimal numbers actually go in that particular order. Like A actually stands for 10, B stands for 11, C stands for 12, etc. Okay, so what I'm going to do here is they're telling me it's a 6-digit long hexadecimal number, so I'm going to lay out my little template of 6 numbers. And this is going to be how many choices I have for each of those 6 digits. So they say that it has to begin with one of the digits 4 through D. So 4 through D is, let's see, how many numbers are in there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that is 10 digits are 4 through D. Okay, so for this first digit here, I have 10 choices. Because 4 through D is 10 digits. Okay, and then what else do they tell me? They say it has to end with one of the digits 2 through E. So 2 through E is going to be, let's see, that looks like 14. No, sorry, that's going to be, I missed the 0 on the other line. That's going to be 13 digits. So I'm going to have 13 choices because 2 through E is 13 digits. Okay, so that's the number of choices that I have for the first and the last digit. And then what am I going to have for these others? So for all of the other digits, they haven't told me any restrictions. So these can be any of the 16 digits. So this is going to be 16 here in all of these other places. I have 16 choices. So you can figure out what this is with a calculator. Personally, I don't really care exactly whether you simplify your answers or not. I'm just going to leave mine like that because they didn't tell me how to simplify it. Okay, so go ahead and pause the video and do part A, and then check your answer in the back of the book. Okay, so let's do another combined example and homework problem. So this 2 parts here, those are your homework, and then this one is going to be the example. So a coin is tossed 4 times. Each time the result H for heads or T for tails is recorded. An outcome of HHTT means that heads were obtained on the first 2 tosses and tails on the second 2. Assume that heads and tails are equally likely on each toss. Okay, so for part C, what is the probability that exactly 1 head occurs? All right, I think I'm going to need to do part A first in order to do that because I need to know how many outcomes are possible in order to do the probability. Okay, so let me do part A first. So part A, how many distinct outcomes are possible? Okay, so just from any 4 results, so here's my 4 blanks for my 4 coins, and I can get either heads or tails, so 2 choices for each of these. So what I'm going to get here is I'm going to get 2 times 2, so it's times 2 times 2, and that is going to be 16. So the answer to part A is 16. And then now let me do part C. So what is the probability that exactly 1 head occurs? So I think I'm going to need to actually write out what those outcomes would be. So if there's exactly 1 head, what are the elements of this event? So exactly 1 head, I could have gotten the head first, or I could have gotten it second, or I could have gotten it third, or I could have gotten it fourth. So this is a situation where it really won't help me to do the multiplication rule to try to figure out how many elements are in this event, because I don't know exactly where that head is supposed to occur at. Yeah, so in this case, I'm just going to have to count it that way. So my probability here then is going to be, probability of the event is going to be 4 over 16, which is 1/4. Okay, so go ahead and pause the video and try part B, and then check your answer in the back of the book. Okay, so let's try another example. So A and B, that's going to be your homework, and D is also your homework. And then I will do part C as an example, and also E as an example. Okay, so let's try part C. Suppose that in a certain state, all automobile license plates have 4 letters followed by 3 digits. Part C, how many license plates could begin with TGIF? So we really just need those 3 letters that are at the end of the license plate. So I'm going to put 3 blanks. And then we just have to think about how many choices we have for each of these. And it hasn't given us any restrictions other than that it's 3 digits. So we can use any of the 10 digits. So I'm just going to put 10 for each of these. I have 10 choices for my first digit, 10 choices for my second digit, 10 choices for my third digit. So this is going to be 1,000. Okay, part E is a little more interesting. How many license plates could begin with AB and have all letters and digits distinct? So if it begins with AB, then we need 2 more letters, and then we need 3 digits. So this is going to be a letter. But remember, they said that all letters and digits have to be distinct. So we have to use a letter that is not A or B. So how many letters are not A or B? 24. Okay, then for the next one, we need to pick another letter that is not A or B. So a letter that is not A, B, and also it has to not be the letter that we just picked on the previous blank. So it's not A, it's not B, and not previously chosen. Okay, so not chosen right over there. So we're only going to be having 23 letters left. Okay, so that's for the letters, and then for the digits, so first we have 10 to choose from. So this is just any digit. But then for the second one, we're only going to have 9 to pick from. So any digit not previously chosen. So we can't choose the same digit that we just chose. So there will only be 9 left to pick from. And then for the next one, it's going to be 8 because, again, it's any digit not previously chosen, and so far we've chosen 2. Okay, hope that makes sense to you. So this is my answer. It's just 24 times 23 times 10 times 9 times 8, and you can put that into a calculator, or you can just leave it like that. So go ahead and pause the video and do part A, part B, and part D. Okay, so now let's go over the concept of permutations. A permutation of a set of objects is an ordering of the objects in a row. For example, there are 6 permutations of the letters in the set A, B, C. So here I've just listed them for you in alphabetical order. So first there's ABC, and then ACB, and then the ones that start with B are BAC and BCA, and then the ones that start with C are CAB and CBA. So that's all 6 ways of rearranging the letters A, B, C. So we can actually use the multiplication rule to figure out how many ways there are to order n objects. So if you break down the ordering into a series of steps where first you pick the object that goes first, and then the object that goes second, and then the object that goes third, and so on and so forth. So for your first object, you have n choices. You can just pick any of them. And then for your second object, you've already placed one of them down in an order, so you only have n minus 1 choices left. And then for your third object, you only have n minus 2 choices left, and then so on and so forth. By the time you get down to the last 2 objects, you'll have 2 choices for the second to last one, and then you'll only have 1 choice for the object that goes last, because that would be the only one that hasn't been put down yet. So if we use the multiplication rule, then we get that there are n times n minus 1 times n minus 2, and dot dot dot, all the way down to 2 times 1 ways to order the objects. And I hope that you remember this notation right here. This is n factorial. So the exclamation point is read factorial, and it just has this formula right here. So there are n factorial ways to order the objects. So theorem 9.2.2 is just telling us that for any integer n with n greater than or equal to 1, the number of permutations of a set with n elements is n factorial. Okay, so let's look at some examples of how we could use this. So how many ways can the letters of the word, sorry, I'm doing those 2 are your homework, and then I'm doing this one. Okay, so how many ways can the letters of the word algorithm be arranged in a row if the letters G-O-R must remain together in order as a unit? So the way you want to think of it is, think of the objects that you have that you're arranging. So here are the objects. Let me draw you a little picture. So you have the A, and then you have the L. Just imagine you've gotten them written on like cards or something. And then you have GOR, and that is all one object. And then you have your I, you have your T, you have your H, and you have your M. And so you've got all these objects, there's 7 of them, and then you're just gonna arrange those in a row. So there are 7 objects, and there are gonna be 7 factorial, which is 7 times 6 times 5 times 4 times 3 times 2 times 1 ways to order them. And that's it. So go ahead and pause the video and do part A and part B and check your answers in the back of the book. Okay, so now let's talk about the concept of permutations of selected elements. So not all of the elements, just some of them. So oftentimes we want to know how many ways there are to choose and arrange R elements from a set of N elements. This concept is really crucial to being able to build up and model more complex kinds of events than the ones that we've seen so far. So we have a special vocabulary for this. An R permutation of a set of N elements is an ordered selection of R elements taken from the set of N elements. The number of R permutations of a set of N elements is denoted P of NR. So this is function notation. It's a function that has 2 inputs, so it's got the little comma between them. Another common notation is this one right here. You might have seen that before. I think that might be the notation they use in like AP statistics, for example. Okay, so we have a theorem here that tells us actually how to calculate this P of NR thing. So if N and R are integers, and 1 is less than or equal to R, and R is less than or equal to N, then the number of R permutations of a set of N elements is given by this formula right here. So P of NR is written like this. So it's very similar to the factorial, but it does not go all the way down to 321. It actually stops, and in particular, it stops after exactly R factors. And we'll talk about why that is on the next slide. And then the other equivalent formula that will give you the exact same answer is this one right here. So you have n factorial on the top, and then you have n minus r factorial on the bottom. So now let's talk about why these two formulas are what they are. So why the formulas work. So here I just put them, I just copied and pasted that part up there again. So if you think about what you're doing when you're taking R elements out of your set of n, and you're doing that in a very particular order, you can imagine it like this little diagram right here. So you're taking out R elements, so you have 1, 2, 3, ... R places that you want to place them in order. And so your pool of available elements has n things in it, which are right there. And so for the first element, you have n choices, because you can choose any of those n things that are in your pool. So this will be n right here. Okay, and then for your second element, you have n minus 1 choices, because you've already taken one thing out, so you only have n minus 1 things left in there. Okay, and then for your third element, you have n minus 2 choices, because that's how many elements would be left in your pool. And then you just keep going like that, and if you count very carefully, you can figure out that there are n minus r minus 1 will be left when you're choosing your rth object to be placed down. Because if you think about it, this is like n minus 0 right here, and then you have 0, 1, 2, and then ... So if you're starting with 0, then you stop at r minus 1 to make sure you've done this r times. Okay, so that's why that is the formula right there. It's just the multiplication rule. And another way to think of it is, if you look at the second way right down here, what's happening when you put the factorial over the other factorial is, if you would write out that factorial that's on the top, the n factorial, write that out, write it down to this factor, and then keep going from there, keep going, all the way down to 321. And then you do the same thing for the n minus r factorial that's in the bottom. What's going to happen is that all of those factors starting with n minus r are going to cancel out. And so that's going to leave you with exactly the same thing that you had in the first example up there. Okay, I hope that makes sense to you. It's a little bit complicated, but you can work it all out if you want to think about it a little more deeply. I must say that I was really pleased to see that the textbook author had included an actual fluffy cloud in a math explanation. As far as I know, I'm the only mathematician who uses fluffy clouds in my work, so I was really excited to see that Susanna Epp had also done this. I feel like she's my soul sister now, although I am still mad at her for using the capital N notation for cardinality. Okay, let's do an example. Okay, so let's do an example. So this is going to be the example here, and then this one will be the homework. Okay, so write all the three permutations of S, T, U, and V. So I think the easiest way to do this is actually going to be to make a tree. So maybe I'll make my tree sideways this time. Let's see how that goes. It got a little cramped last time. Okay, so I'm going to start by picking one of the four letters. So I'll just do S, T, U, and V. And then after that, I have three left that I can choose. So I'm going to branch into 3, 3, 3. I can already see this is also going to be cramped. Oh well. So let's see. If I picked S first, then I can do T, U, or V. If T is first, then S, U, or V. If U is first, then S, T, or V. And if B is first, then I can do S, T, or U. Okay, and then for my last, I have 2 to pick from. So this is a lot of permutations. Okay, I think this is 24, right? Okay, so if I did S and T, then I can do U or V. If I do SU, it's T or V. SB is T or U. If I do T and S, then it is either U or V. If it's T and U, then it's S or V. T and V is S or U. US is going to be T or V. UT is going to be S or V. UV is going to be S or T. VS is going to be T or U. VT is going to be S or U. And then VU is going to be S or T. Okay, so if I write out the final outcome from all of these, this one is STU, and then it's STV, and then SUT, and then SUV, SVT, SVU, that's a TV show, TSU, TSB. Sorry, my U's and my B's are not that different. Oops, that one's neither. I guess I can't write and talk at the same time. Okay, that is a TUS, that is a TUV, TVS, TVU, UST, USB, UTS, UTB, UVS, UVT, VST, BSU, VTS, BTU, BUS, and BUT. Okay, so that is all of the 24 three permutations of STUV. So yours is a little bit easier, so go ahead and pause the video and try number 35 and check your answer in the back of the book. Okay, let's do one last example and homework problem. So the part A and C here, those are your homework. And then part B and D are going to be examples. Okay, so part B, how many ways can the 6 letters of the word algorithm, how many ways can 6 letters of the word algorithm be selected and written in a row? Okay, so for part B here, the word algorithm contains, let's see, 9 letters. So we have 9 letters. And we're choosing, and that's not how you spell choosing. We're choosing and arranging 6 of them. So what we're doing here is we're actually calculating P of 9, 6. And so there's a few different ways you can calculate this. You could do it as 9 factorial over 9 minus 6 factorial. Or you can just write out the 6 numbers of choices that you would have. So you'd have 9 choices for your first letter, and then 8 choices for your next letter, 7 choices for your next letter, and then 6 choices, 5 choices, and finally 4 choices for the 6th letter. So you can do it like that as well. Either of these is fine. I'll just circle that one. All right, and then for part D, so how many ways can 6 letters of the word algorithm be selected and written in a row if the first 2 letters must be OR? So we're going to have O, R, and then we're going to have 4 more letters. So originally we had 9 choices, but we've taken 2 of them away. So here we're going to have 7 choices. And then here we're down to 6 letters, so we would have 6 choices. And then we would be down to 5 choices. And then we would be down to 4 choices. So this is going to be 7 times 6 times 5 times 4. So you get that. Another way to think of this is you think of those 7 letters that were left over from the word, and you're choosing and arranging 4 of them. So this is also P of 7 comma 4. I'll just circle that one that's the most simplified. So you could also, of course, do it like this: 7 factorial over 7 minus 4 factorial, like that. Okay, last thing I want to say is about doing P of n comma r on a calculator or a computer. So pretty much every type of math, every computer or calculator math system will do this. Wolfram Alpha will do it, Excel will do it, your TI calculators will do it, or your Casios. Even most scientific calculators, believe it or not, will do it. Like, this is my scientific calculator that I use, and it has written in really small font right there is the letters N, P, R. So even those scientific calculators will sometimes do it. I put the instructions here for the TI-84 Plus because I think that's the most common calculator you guys are using. And then if you don't have a calculator at all, of course, you can do it on Wolfram Alpha, just like this. And if you have something other than a TI-84, just Google how to do it on your model of calculator. So keep that in mind when you're doing these problems. You don't need to actually multiply lots of numbers together. You can just pop this into a calculator. All right, so that's all for today, guys. I think we finished up in a pretty good time. So I'll see you next time, and we'll do some more counting.